Okay, so what we have here is a graph, right? And what we're set out to determine whether it has an Euler circuit, where an Euler circuit is possible, and if not, can we Eulerize it, which means add enough edges so that we are guaranteed to have an Euler circuit, right? Now again, an Euler circuit is when each edge is traveled, right, without any duplicates. Okay, now we did cover a couple of theorems, right, in the earlier part of this module that set out the conditions to have an Euler path and an Euler circuit. Right, now for an Euler circuit, right, what is required is that all vertices have even degree. All right, if all vertices have an even degree, then an Euler circuit will exist. All right, now looking at this, we see, all right, well, I do have some issues here in terms of having even degree vertices. Vertex A has degree 3, vertex D has degree 5, and vertex E and F both have degrees 3. Okay, so we set to Eulerize these, right? Now, the Eulerization process says to, if possible, connect the two odd degree ones with an additional edge, right? Hence making them both even and solving our problems of having an odd degree vertex. All right, now if a straight path is not possible here, then what we do is we do the shortest, or a path to get through through both odd ones. Okay, like for instance, what I mean here is, let's say that here for A, we can simply draw another edge here between A and D, hence solving our problem here, but we are also could do something like this, right? C and D. All right, and we see there, right? Okay, and we see that this solves our problem, where now we have this is of degree 4, and this is of degree 6, so it's even. All right, and when we say efficient, we say, well, we added 2 edges, right? Can we do it with less edges? In this case, 1. All right, as it turns out, yeah, we actually can do that, right? If we set out here, what if I went from here? Here. Let me highlight this one. Give me a second here. Okay. All right, and then we could see here, right, we're able to have the same outcome where we have all of our odd vertices now become even, but only by adding 1 additional edge. All right, now keep in mind when we add edges, we want to make sure that we are not connecting to vertices that weren't previously connected, right? So for example, here from C to F, right, we are not allowed to do that. That changes the graph, right? Remember, when we are adding a vertex connecting, when we add an edge connecting two vertices, right, that already have a connection, what that is kind of signifying is that we are kind of going over our path, right? We're retracing our steps, right? We're visiting, we're going through that same path twice. Okay, so that gets us even degree in A and D. Now we still have the issue with E and F here, but again here we can go ahead and connect those here. Let's see, where is that one? There we go. All right, and now we can add that edge, right, going over E and F. All right, now that solves the problem of us having of us having any odd numbered vertices, right? They're all even now. So our theorems from the earlier part of the module state that if we have all even, if the vertices have all even degree, then an Euler circuit will exist. Okay, and that is the process of Eulerization. All right. If we want to find that path, we can look at the previous topic in the module, the Fleury's algorithm. It gives us a way to determine a Euler circuit. All right.